Alrighty, so hello and welcome. Let me charge my headset actually over here. Oh man, I'm tired. I had a hard time sleeping last night. I have so much anxiety. I shouldn't. It's kind of a sin. I should trust God. I should trust God, but I still struggle anyway. Yeah, so hello and welcome. Howdy. I wanted to take a look at one of the problems on LeetCode. So the problem that I was looking at the other day, I had some ideas, some thoughts on what I could do to optimize that slightly, what I had written. And I think I'll code that later. Maybe not now, but later, maybe later today I'll look at it again, come back to it. There's like a lot to spend my time on right now, like competitive programming, like knowledge, just like learning, some articles, LeetCode problems, and the Bible. Actually, the Bible really should be at the top of that list, but I'm really conflicted because I need to find a job. So I've been kind of trying to focus on that too. I'm not really sure what the best thing to spend my time on is exactly, but some variation of these things I think is what I'm supposed to do. So anyway, so let's take a look at a problem. Let's do this in C++ today. Maybe I should be practicing in other languages too. I don't know. I like C++, but it may be the case that I should practice in something else. So I haven't read this problem yet. Let's see what it says. Integer array nums, got a lot of upvotes. Turn the number of triplets chosen from the array that can make triangles if we take them as side lengths of a triangle. So 2, 2, 3, 4, 3. Valid combinations are 2, 3, 4 using the first 2, 2, 3, 4 using the second. 2, 2, 3. Oh, that's interesting. Oh, wow. Whoa. 4, 2, 3, 4. 1,000 numbers between 0 and 1,000. Oh, that's an interesting question. I don't know. I don't know the solution to that. Obviously, there's a cubic brute force solution where you walk through every pair, every triplet, and then assess it directly whether or not these could be the lengths of a triangle. Although I don't even know the maths offhand to determine if 3 lengths could be the length of a triangle. I think you can as long as I think you can always do that. Any A, B, and C could be the lengths of a triangle, positive or obviously positive, non-zero, as long as they have what they call a triangle inequality. So the sum of 2 of the sides does not exceed one of the other sides. So 2 plus 3 is not greater than 4. 3 plus 4 is... Oh, wait. No, I think it's the other way around. I think the one side doesn't... okay. So any given side will be less than the sum of the other sides. So 2 is less than 3 plus 4, 3 is less than 2 plus 4, and 4 is less than 2 plus 3. Yeah, that's the way. That's a triangle inequality. Now, is there a way to do this more efficiently? So actually if we take all triplets like that, this won't work. Also, counting. Yeah, so we probably could do this rather efficiently. There should be a way, I think. We kind of got to ponder how we could do this more efficiently, though. Certainly, so I think for each number, you have 2 other choices, and choose 2 other choices, I suppose. And if we go sort of left to right, not exactly n choose 2, but I guess it would be n minus I choose 2. So of the remaining elements that we haven't looked at yet, you can do it that way, and maybe you can do that in linear time. The trick though is, and we might be able to do this sorting the list first. How are we doing on time? 5 minutes. Okay. I think the trick is going to be any other number that you might consider, right? Well, the triangle inequality has to hold for all of the sides, so it's got to be. Maybe it'd be easier to exclude certain possibilities. By the way, counting all of the possible triplets is kind of a tricky thing too. It's like the sum of. It's like n choose 3. Sort of like n choose 3 different triplets. But amongst those triplets, you have. Yeah, you can't pick any. You can't have a side of any triangle that is larger than the sum of the other two. So 2, 2, 4 would not work, right? So everything. So okay. I mean, you could maybe do like something n squared log n, and say, sort the list and then pick any 2 elements, and then it's a tricky thing though, because it's a good question. Let's see why they uploaded it. It's a challenging question. Any elements that you would pick, it would need to be the case that A plus B is greater than or equal to C, and A plus C is greater than or equal to B. So suppose we picked some A. Oops. We would have A plus B is got to be not greater than or equal to, strictly greater than C, and A plus C is greater than B. And so does that imply anything about B and C that we can use to filter on how many things we want to look at? So I'm going to use some maths to optimize our algorithm, really. That's what it comes down to. So A is greater than B, I guess it would be C minus B. Also, A is greater than B minus C. So A is greater than the difference, the absolute difference of B and C. Interesting, and that's got to be true in all three situations. So A is greater than the absolute difference of B and C. A is greater than the absolute difference of B is greater than the absolute difference of A and C is greater than the absolute difference of A and B. Okay, interesting. So it does give us something for if we picked a pair of 2 values, which values we can actually select. We can do that in logarithmic time. So we can do O of n squared log n to find out which index for A is possible, right? We can use an upper bound, or it's got to be greater than, not greater than equal to, but strictly greater than. So I think it's actually the upper bound. I think the lower bound is greater than equal to, and then the upper bound is greater than. So we're looking for greater than. How are we doing on time? Okay. Oops. Yeah, so sorry, I'm just thinking I watched a video of pastors making jokes. They got some funny ones. They got some really funny ones. All right. So we're looking for, so we could do O of n squared log n time. I got that, right? I'm pretty sure we could do that. We can do a you can loop through all of the values for B and C, or just even A and B, and then take their difference and then find all of the other values that would be larger than that difference. Now, the tricky thing about that, though, is that I don't actually know if first off, actually, I'm not sure if that's O of n squared log n, because even though A being greater than the difference between B and C does not necessarily imply these two other things as well. So actually, it's not necessarily O of n squared log n. I take that back. Yeah, because you could have a situation where like the difference between A and C could be larger than B, right? So actually, this is the triangle inequality. This is a really interesting question. Not obvious at all how to solve this. If more efficiently than cubic. Cubic time would be too slow if we did this. Even though there's only 1,000 numbers, cubic would be very, very slow. I don't know. How can you solve this in a way that's faster? Maybe you could take like average differences, something like that. A plus B plus C is greater than the differences, the sum of the differences. A minus B plus B minus C. Yeah, you can maybe think of it that way. What are the differences between these? 1, 1, and 2. So 1, 1, and 2 gives you 4, and then A plus B plus C is quite a bit larger. But that doesn't work for 2, 2, and 4, right? You get 0 plus 2 plus 2 is 4, and then obviously 4 plus 2 plus 2 is greater than 4. So that actually is not very useful. This doesn't capture everything. So A is greater than the absolute value. So A is greater than B minus C, or negative A is less than C minus B, depending on which one's which. It's actually, this could be positive or negative, doesn't really matter. Let's do this. Let A be less than or equal to B, less than or equal to C. All right, let's do that. Let's do it that way. Then you can say absolute value of B minus C is then C minus B. Absolute value of this makes things a little bit easier to work with. C minus A. Absolute value of A minus B is B minus A. Right. So we could say, so A is greater than C minus B. B is greater than C minus A, and C is greater than B minus A. All right, now if we add all these together, we get A plus B plus C is greater than C minus B plus C minus A plus B minus A. Which gives you A plus B plus C is greater than negative A plus C. Interesting. So B cancels, B cancels. It's 2C. 2C, B's cancel, minus 2A. Yeah. Let's get A plus B plus C is greater than 2 times C minus A. All right. Interesting. I don't know how far I'm going to get with this problem. Is that true? So we took C minus A, So, well, this is always going to be larger than that though, right? Like 2 plus 2 plus 4 is 8. That's always going to be larger than C minus A is 2. 2 times 2 is 4. No, man. 2 plus 2, 2, and 4 did not work out. So that's not enough, not strong enough. And that doesn't really help us too much. Well, that is to say that C, so I guess A plus B is greater than C. And also C is greater than B minus A. Maybe we can make this the other direction, right? A plus B is greater than C. A plus B is greater than C again. On the other side. And then again, A plus C is greater than B. Okay, well, these are the same. That's interesting. So we really only have A plus B is greater than C. And A plus C is greater than B. Is that all you really need? If you had 2, 2, and 4. Yeah, 2, 2, and 4 doesn't work for this one. And then A plus C is greater than B. So that's really interesting. So you take some A and you select a B. For each B that you could select, the only C's that you can select are, or you can only select a B and C pair for A such that this is true. For A is greater than C minus B and A is greater than B minus C. This is a positive number. This is true. So this is true by default. Vacuous are just true by the assumptions we've made. Right, if we make A, B, and C, so A is less than B is less than C, less than or equal to, then this and A is non-zero. B is strictly less than. So this is just always true. So this part we don't actually need. So this is really the only part that matters. A plus B is greater than C. Okay, so we're looking for all pairs that satisfy A plus B is greater than C. So we can, we can write that directly and see how far we get. Generate 1,000 numbers locally here. This question might take us some time though, because I don't actually know the answers. So you can do for int I equals 0, I is less than nums dot size plus I. For int I equal j equals 0. Excuse me, we're going to use standard vector int v of nums dot begin, nums dot end. And then we're going to say, we use v actually for everything here. We're going to use a copy. J is less than v dot size. We also want j equals I plus 1, I think. Yeah, j equals I plus 1. Plus j. K equals j plus 1. Let's do kind of a round robin type of thing. We'll say if, so we'll say int a equals v of I, b equals v of j, and c is equal to v of k, and we say, so we can just prove that this is going to take a while. And we're going to sort. So this will guarantee that A is less than or equal to B is less than or equal to C. We sort V first. In C++, it's pretty straightforward to sort this. And now we have A, B, C, and we say if A plus B is less than C, is greater than C. It's going to be greater than C. Then we increment our count. Okay. All right. So we can try this. And we can say, let's actually run a local subroutine here. We want, so we have gen, I have this kind of, we want to generate random numbers. Actually, yeah, let's generate random numbers. So let's copy our gen characters program to gen numbers program. And gen number, I just want to prove that cubic time is too slow for this. Uniform distribution, we can actually use the arguments for this. Okay. Okay. And at least one should be at least two integer arguments. I'm gonna recompile that one, by the way. Yeah, we're gonna say G++ gen characters output to gen random characters to executable. Okay. I just noticed that the there we go. Okay, I just noticed that program, the text, the help text, I guess, isn't quite what I want. So gen numbers is similar. Now we want two arguments. We're gonna pick three arguments actually. Three. We're gonna say it's actually gonna be argv1 to argv2 and then argv3. Gonna generate random numbers, and these are characters, but we actually want numbers now. So just say dgen, and we actually also want we want to format this in such a way that it looks like the output to, so it'll be this and another dgen, and it's going to have space. And what we're going to do is actually, what we want to do is, these aren't going to be on new lines, they're all going to be just one line, but we're not going to add a comma for the last. So if I equals total nums minus 1. So if we say, so if it's less than total nums, then whoops, did that wrong. Yeah, so we want to print a new line character and a space if we know there's more coming. If the last character, the last integer we print, we don't add a comma and a space. And then at the end, we're going to add 2 more pieces, which is closing brace, closing bracket, and then a new line character. And we can compile random numbers, executable, see if that compiles. It does. And now we want numbers between, we said it's going to be between 0 and 1,000. And there's going to be 1,000 numbers. So 0, 1,000, 1,000. One integer argument. Okay. Oh, I did that wrong. Yeah, gen numbers now. Oh, it didn't compile. Okay, I thought it might not compile. Yeah, okay. I was gonna say, I was like, usually it doesn't compile the first time I try to execute. Try to compile. Usually there's some error. Oh yeah, these are strings, right? Okay, makes sense. Yeah, I want to use standard STY. Forgot. It's my mistake. We can do low bound. And upper bound or high bound. And this is just low bound, high bound. See if that compiles. There we go. Okay. And there's always some error. Typically it makes some kind of error. 0, 1,000, 1,000. Oops. Oh, that's not what I wanted. The number of arguments has got to be 1 is the program you're calling, and then there should be 3 more, so 4 should be 4 total. As I said, there's always some kind of error. There we go. Hey, look at that. Sweet. So you can pipe this to a file now. Oh. Oops. That wasn't what I meant to do. That's funny. Oh. Actually, it's interesting is you can actually. Here we go. Copy paste this way. Now try this. I think it should TLE. The whole point was just to show that this is too slow. This program. Or to show it's not correct. Yeah, TLEs. Yeah. Right. Just not going to be good enough. How are we doing? 30 minutes? Okay. We want something else here. Let's try, let's remove TT and let's try random numbers. Let's go, instead of 0, 1,000, 1,000, let's do like, let's do like 300. And the reason why I want to do that is I want to the reason I want to do that is I want to test if this, if this is sufficient criteria. This will be correct. It'll be slow, but it might still be correct. Oh, there we go. Yep, still correct. Okay. It's too slow, but it is correct. So that's interesting. What point does it start to become too slow is the question. Because I might be able to get away with this if it's only like, you know, a few thousand or something. Like if it's like 950 is good enough kind of thing. Just curious. Let's see what this does. It should TLE. Yeah, okay. Let's try something else. Let's try like I don't know, 600. A little more familiar with the commands in Windows for the text editing. All right, so it's somewhere between like 600 and 950 that it breaks down. But this is interesting. I'm wondering a few things. One, if you can actually use a frequency map for the number of numbers because the range is constricted here, and you might be able to process this directly in that way. But actually, I think even that breaks down too, because you know it could be one of each number. It could be 1,000, and then you still have a cubic in terms of 1,000. So yeah, it's not necessarily help. It doesn't necessarily help us too much to take advantage of the bound on the numbers themselves. So okay, so we need to do something clever though. Like at least we have a correct algorithm. That's nice. So this is really the only check that we need to make is we need to find each triplet such that A, B, and C are in sorted order, and A plus B is greater than C. The two smaller sides are larger than larger. The sum of the two smaller sides is larger than the larger side. I thought this is like a trivial thing, look at this question first, and I've even thought about this in the past, or seen something similar to this in the past, but it's not a trivial thing to do this efficiently. It's not. You could maybe you can maybe choose for each A and B, you can find a C, like all of the C's that are smaller, I guess, right? Or alternatively, for each A and B selection, you can find sort of on the right side all of the values of C that are to the right of B. You could do a logarithmic search, I think. So instead of doing cubic time, this could be semi-quadratic, quadratic. I think you could do it that way. And square log n. So for each AB pair, you can find all of the values, all the C values that are, let's see. You're looking for all the C values that are larger than B, but smaller than A plus B. Okay. Interesting. Yeah, you could do that in logarithmic time. You could do a binary search to find, but that's kind of tricky, isn't it? So you're looking for, yeah. So I guess you start in the array after B, and you're looking for values that are smaller than A plus B. Well, I mean, you could find the first point that's, I guess, the lower bound that's greater than or equal to A plus B, and you take right before that. Right, the lower bound is the first. Yeah, so C is less than that. So yeah, the point right just before. Guess you could do it that way. Do a lower bound on A plus B from B plus 1 to A plus B, and subtract 1 on so actually you could do A plus B minus 1 and do a lower bound. I think that's the way to do it. So it guarantees that all the values you're looking at are between, they're greater than, yeah. So yeah, I think that's the way to do it. And then you get the index in the array that is, and there are some cases that are 0, and then that index you can use to count the number of numbers in there. Yeah, I think you could do that. We could try that. Slightly speed this up. That's 40 minutes, so we were thinking about this. Pretty challenging. Let's see, but I think we got it. I think we got the idea. So we can do upper bound on use binary search, find, count the indices. Variable. Binary search to count the indices. So we can say, this is a slight optimization here, but I think it's sufficient for this problem, but it's not going to be, it's not a very good optimization. It's not like, this is not a very fast way to solve this problem. It's just probably fast enough to submit the solution. So we can do standard upper bound, no, lower bound on, I just have to double check. That's nice, the STL works nicely here. We're looking for first, last value. Yeah, I think it's that simple. So can do, first we're going to say it's going to be I guess B plus 1, so it would be something like it's something like v dot begin plus I is B is j plus 1, right? To v dot end. And it's going to be A plus B minus 1. Yeah. And we're going to say auto pointer is equal to this. And then we're going to say int index is going to be pointer minus v dot begin. And then we say ret plus equals, so we're going to take the difference between this index and the index of, so we define these two indices now. B is at index j, it's minus j, I think plus 1. So we want all the values minus, and this is going to be j plus 1. Yeah, I think that's why it's going to get a little confusing. So It's all the values between these two bounds inclusive, right? So this is the first time, so that a plus b minus 1, we take the first value that's greater than or equal to a plus b minus 1. Now that's confusing as heck. Yeah, the first time that we're greater than... So the tricky thing here, though, is that this might not work the way we'd like it to. There are a few things here that are kind of tricky. We actually want a plus b, and I'll explain. So we're going left to right, we're going to find the first time that a value in the array, or it could go off the edge of the array, first time that a value is greater than or equal to a plus b. Everything to the left of that should be less than a plus b, right? Now, I was thinking we do a plus b minus 1, but actually that won't really do what we want either. So we really we want to subtract 1 from the pointer, ultimately, and potentially, right? Now there are a few things, like one, this could be the end pointer. This could go right off the edge. Like the quote-unquote subtracting 1 doesn't necessarily make a lot of sense. But what we want is, so we find that index of that value, and we're going to say take that index, subtract j minus 1 plus 1. So we're going to include that value and include the j plus 1 value, and then we're actually going to subtract another 1. So we end up with an int minus j minus 1, and we'll say int x, we'll say index minus j minus 1. So if x is greater than or equal to 0, then ret plus equals x. So it's possible that this actually becomes like a negative value. That's kind of what we're getting at here. Now, I don't know if this is going to be correct. That's the thing, is that there are some issues with this. Oh, a plus b. Oh, okay. Okay, let's try that. How are we doing on time? Yeah, you got a few minutes. Okay. Oh, it's correct. Whoa. I was not expecting that. Really? Wow. What? What? It's actually correct. Huh. Not expecting that at all. Not even remotely expecting that. I like it. It's a notepad-exe. Let's see how efficient is this one, the second one. Okay. It's not only correct, but it's efficient too. It's very efficient. Really? Okay. Wow. I don't know. No kidding. Can we just do a bunch of these test cases, maybe? I don't really know. Maybe get some duplicates in there. Do 5,000. Try to make it really. Try to really make it stress test here. Should give me a invalid test case, I think. Let's do, okay, fair enough. See if we can get rid of that test. Yeah, we get rid of all of them. That's fine. They seem to all be correct so far. What I want is some duplicates. Let's do, okay, 1,000 numbers. We're gonna go from 1 to like 100. No padded now. Can't seem to type that in correctly. 1:09 p.m. Okay. All right, let's go for it. I don't know. There's got to be some test cases I missed somewhere somehow. Nervous here. Hey, it worked. Okay, sweet. Okay. Hey, look at all these hards, man. The hards usually are like slight differences from the easies, or the mediums rather. slight modifications. So okay, how much time we got here? So yeah, I got kind of wrecked by this problem. I mean, we did it, you know, but we just barely made it. We're like the bottom 5% here. These are problems that are like, I don't know. I could come up with a solution, something, but it's not perfect. You know, it just makes it. Just makes it. There's always some trick to these that are like some slight thing that you haven't thought about that you can use. You have to think about it for a while though. Come up with it. That's all these questions are. All of them are like that. The hards I think are like that. I think they basically you won't be able to solve the hards. The hards are usually like almost the same thing, but you won't be able to solve them without using some trick, some optimization that you probably don't know about. So there you go. There's one approach. Nice. Glad that worked. It's an interesting way of approaching it, but yeah. Okay. All right. Oh, that's what that does. Okay. So we can study the. We can spend some time and study the. So yeah. So thank you for watching that. Those of you that did. And what's neat is we can go over now the discussion and see, like, now that we were able to solve this but inefficiently, what's the more efficient way to do it, because I just don't know it. It's gonna take way too much time. O(n) squared, O of 1 space, 3-sum, similar solution, O(n) squared solution, 3-sum, 3 pointers, sort, 2 pointer solution explained, O(n) squared, simple and clean, 2 pointers, clean and concise. And squared login using bisect left. Yeah, I used the same thing. 3-sum smaller, similar. Oh, okay. All right, let's do the C++ O(n) squared. So we sort. And we say count as 0, and we go n equals nums.size, k equals n minus 1, k greater than 1, decrement k. Okay, interesting. So s is nums.size. Interesting. N equals nums.size, k is n minus 1. Int I equals 0, j equals k minus 1, while I is less than j. Any value x between I and j will satisfy s nums plus s nums j greater than s nums k. Because s nums k is greater than s nums j is greater than s nums x greater than or equal to 0, they will always satisfy the other. Oh, interesting. Okay, I see. Because, so any value x between I and j will satisfy here. And because this is greater than this, and this is greater than that, they always satisfy these two greater than this one, and these two greater than that one. Yeah. This was, right. So, I less than j, you would, that's really interesting. Python ideally. This is so smart. Yeah, it's really smart. How did we do? So I is 0 and j is everything between. Okay. So how do you know that nums of I and nums of j, if you add these two, they're going to be greater than k? Saying if that's the case. So this is what they call like sliding window, right? So we loop for every basically largest value, right? Every c value on the right side. Right? We're going to loop from right to left. n is, well, I don't really think you needed to do this, right? I don't think n is used anywhere in here, so you could just do k. All right, so start from the rightmost index, and you're going to have a pointer on the left and a pointer on the right, and you say, okay, oh, I think that's why he did k and n. No, k could just be, no, that's fine. So pointer on the left, pointer on the right, you have this window. You say, all right, if we add these two numbers together and they're greater than k, then all the sums in between will be greater than k, necessarily, right? Because from the left to all the way to k, all the way to j, all of those are going to be larger, right? So then what you can do now, if it's not larger, then you can increase I until it is larger, and then take all of those. And then what you can do is decrement j once you've found all the sums. Oh, I see. Oh, that's super smart. Yeah, man. I don't know. I'm a dummy. I didn't even think of that. That's so clever. That's so much more clever than I realized, than I even thought to do. Okay. All right. So we're actually going to say k equals v.size minus 1, and we're going to say k is greater than or equal to 0. Really, it should be k greater than or equal to, k is got to be greater than or equal to 2, I think. Minus k. Sliding window. We're just going to call it sliding window. Sliding window. Double pointer approach. All right. So let's get rid of. Well, actually, what we'll do. Hold on. Okay. We can say these things. Okay. So for int k equals v.size minus 1, k is greater than or equal to, really should be 2, right? We say we're going to say int I equals 0, j equals k minus 1, right? Going to the left of k. We're going to say while I is less than j, we're going to do the following. If, so take advantage of the fact that if v of I plus v of j is less than or is greater than v of k, then all of the values in between I and j can be used. Pairs satisfy the same condition. So ret plus equals j minus I plus 1, and decrement j. We'll say if v of I plus v of j is greater than v of k, we can actually do that once, do the lookup once. Whew. If the pair doesn't satisfy, slide the left pointer through the window, or yeah, through slide the window. Slide the window up, I guess, or down, however you want to view it. And that's super simple to code. I would never have gotten that without looking at it, looking it up. It would take me forever to think about it. Ooh, wrong though. Okay. Interesting. I think this is not +1. That might be the problem. Yeah, let's go for it. See how we do. I don't know if that's correct. I didn't even test it. I probably should have tested it. Hey, we got it. Okay, not bad. Sweet. Yep, there you go. Yeah. Sweet. Super simple, super concise, way more concise. Yeah, man. Huh. I like that. I like that a lot more than what I wrote originally. That's also a lot faster, as you can see. It's like 10 times faster in these test cases. That's a lot faster. Is it faster to code? Well, it's not faster to come up with. I think thinking about that would take a while, as I mentioned, like trying to think that through. I don't know. What are the 100% solutions? That's probably as fast as I can imagine. I don't even know. Maybe there's something faster than this. I couldn't even imagine. Let's try one more. Maybe there are some slight optimizations in here that they do. Oh wow. Okay, there you go. All right, that's 99%. Okay, what were the other ones? Oh, okay. So out of nowhere, it's just like way faster. Okay. Just out of the blue, it's just really fast. It's like, all right, I don't know. Why would that be so much faster? Who knows? I guess just random. Okay, that makes sense. Yeah, probably you could get 100% if you make this, you sort this as a reference instead of creating a new vector. You just sort this here immediately. Yeah, that's would be a little bit faster, like a few milliseconds. All right, that's probably it for this problem. So thank you for watching. That was really interesting. I don't know, man. I don't know how I would. I've seen many like sliding window solutions in the past. I just kind of tend not to remember them, I suppose. But yeah, there's another question that some other folks reference, the three-sum question, which is related, where you can you can slide pointers down, like you have basically three things added together are supposed to be equal to a value or greater than a value or less than a value. There are things of that nature. So it's like a three-sum problem. It's two-sum, three-sum, and other related questions. But yeah, I don't know. I just don't remember. I don't know. I don't even. That's something I guess I just have to memorize. But obviously, you can solve it the way that I did with a lot. Two values and then find the section. But it's actually better to do three sort of values. Start from the larger one and go down, and then have a sliding window of values. I just didn't think of that. I don't know. I don't know. All right. So thank you for watching. Talk to you soon. Have a good rest of your day. Take care. Oh, I might be streaming later, but we'll see.